Welcome to today's paper reading. Today's paper is titled, A Closer Look at GAN Priors, Exploiting Intermediate Features for Enhanced Model Inversion Attacks. This paper was published on AR14 by Yixiang and colleagues from Harbin Institute of Technology, Shenzhen and Tsinghua Shenzhen International Graduate School, Tsinghua University. Model Inversion (MI) attacks aim to reconstruct privacy-sensitive training data from released models by utilizing output information, raising concerns about the security of deep neural networks (DNNs). Recent advances in generative adversarial networks (GANs) have improved MI attack performance due to their ability to generate realistic images. However, previous MI attacks have limited semantic extraction and transferability. To address this, we propose intermediate features enhanced generative model inversion, IFGMI, which disassembles the GAN structure and exploits features between intermediate blocks, enhancing the optimization space. This method significantly outperforms previous approaches and achieves state-of-the-art results, especially in out-of-distribution scenarios. Deep neural networks, DNNs, have seen significant advancements and are widely applied in various fields such as face recognition, personalized recommendations, and audio recognition. Despite their practical benefits, concerns about privacy and security have emerged. Recent studies have shown risks of privacy leakage, with adversaries potentially revealing private information from pre-trained models. Various privacy attacks have been proposed, including membership inference and gradient inversion attacks. Model inversion (MI) attacks, particularly those leveraging generative adversarial networks (GANs), pose a significant threat by recovering privacy-sensitive datasets. However, the effectiveness of GAN-based MI attacks is limited in scenarios with significant distributional shifts between the target private dataset and the public dataset used for training GAN priors. Figure 1 presents a comparison of our proposed intermediate features enhanced generative model inversion, IFGMI, with baseline methods. In Part A, the first column shows randomly generated images, the second column displays the reconstructed results by PPA, a GAN-based method that optimizes the latent code. The last two columns show the results of our IFGMI and the ground truth images from the private dataset. The blue numbers below the images indicate the predicted confidence by the evaluation model, demonstrating that IFGMI achieves higher confidence scores. Part B illustrates the top 1 attack accuracy of PPA and IFGMI across 4 out-of-distribution (OD) scenarios, highlighting that IFGMI significantly outperforms PPA in these challenging settings. In the realm of generative adversarial networks (GANs), the generator and discriminator are trained concurrently to produce realistic data. These networks can generate high-fidelity images and utilize an intermediate latent space for more controlled image generation. Model inversion (MI) attacks aim to reconstruct private data from trained models, with recent advancements leveraging GANs to enhance the quality of reconstructions. Recent research has further improved MI attack performance, with methods like SecretGen, KEDMI, and VMI enhancing the attack process, and PPA, Llama, and PLGMI introducing strategies to increase attack accuracy and robustness. Figure 2 provides an overview of our proposed IFGMI method. Initially, latent vectors are sampled from a standard Gaussian distribution and are then mapped into disentangled latent codes with semantic meanings through the mapping network. Random augmentation is performed on these latent codes to select the optimal ones, denoted as W*operator, for further optimization. The synthesis network is disassembled into multiple blocks to search for intermediate features, which are successively updated using the identity loss calculated from the target model. Finally, the reconstructed images are generated from the last layer as the results of this process. The methodology of the improved IFGMI for MI attacks leverages a pre-trained style GN2. This includes a mapping network map that transforms initial latent vector Z into an extended W space, and a synthesis network GSYN that generates images from mapped vectors W. The method focuses on intermediate features, performing hierarchical layer searching and optimizing these features within an L1 ball constraint to avoid image collapse. The loss function used is the Poincaré loss lid, which addresses the gradient vanishing problem by using normalized prediction confidence and a modified one-hot vector. In this section, we discuss the experimental setup, including the datasets, models, and metrics used to evaluate the attack performance. For datasets, we used FaceScrub and CelebA for facial image classification, and Stanford Dogs and AFHQ for dog breed classification. The models included various architectures such as ResNet 18, DenseNet 169, ResNet 152, ResNet 101, and Inception v3. The metrics for evaluation included attack accuracy, feature distance, FID, and sample diversity, which are crucial for assessing the effectiveness of the attack method. Figure 3 presents two key aspects of our method's performance. Part A compares the top 1 attack accuracy, ACC at 1, across various settings of L, the number of intermediate features optimized. This comparison helps in determining the optimal number of layers for maximizing attack performance. Part B showcases visual results generated from different end layers, illustrating the impact of layer optimization on image realism and detail. Notably, the case where L equals 0 represents a baseline scenario where only the latent vectors W are optimized, without intermediate feature optimization. Figure 4 presents a visual comparison of reconstructed images from various methods against the ResNet 18 model trained on the FaceScrub dataset. The first column of the figure displays the ground truth images of the target class within the private dataset. The comparison highlights that the reconstructed images from the proposed method exhibit higher fidelity and realism, demonstrating the superiority of the approach in exploiting GAN's intermediate features. Table 1 presents a comparison of our IFG-MI method with state-of-the-art methods against ResNet 18 trained on the FaceScrub dataset. Key findings include significant improvements in accuracy metrics, particularly on the MetFaces dataset where IFG-MI improves ACC at 1 by 15.1% and nearly achieves 100% ACC at 5. Additionally, our method demonstrates a notable reduction in feature distance, outperforming the PPA by more than 10% on the MetFaces dataset. This highlights the superior generalization ability of IFG-MI, especially in datasets with larger distributional shifts like MetFaces. Table 2 presents a detailed comparison of our proposed IFG-MI method against the ResNet 152 model trained on the CelebA dataset. The results demonstrate that IFG-MI outperforms the baseline PPA method across several key metrics. Specifically, IFG-MI achieves a notable 10.6% increase in the top 1 accuracy, ACC at 1, and significantly lowers the FID value when using the Style GN2 model trained on FFHQ. Even when the Style GN2 model is trained on MetFaces, which presents a larger distributional shift, IFG-MI still manages to outperform the baseline with a 38.8% increase in ACC at 1 and maintains competitive feature distances. These results underscore the effectiveness of IFG-MI in leveraging generative priors to enhance image reconstruction fidelity and accuracy. Table 3 presents a comparison of results against different target models trained on FaceScrub, with the public dataset being MetFaces. The target models include ResNet 152, ResNet 101, and DenseNet 169. The metrics evaluated are ACC at 1, ACC at 5, Delta F-ACE, Evil, and FID. The IFG-MI method consistently outperforms the PPA baseline across these metrics, particularly in ACC at 1 and FID, demonstrating its effectiveness and superiority in various settings. Table 4 presents the results of an ablation study conducted on the ResNet 152 model trained on the CelebA dataset, using FFHQ as the public dataset. The study examines the impact of removing intermediate feature optimization, IFG-MI, and the L1 ball constraint, IFG-MIL, from the IFG-MI method. The metrics evaluated include ACC at 1, ACC at 5, FACE, Evil, and FID. The results show that the full IFG-MI method, which includes intermediate feature optimization and the L1 ball constraint, achieves the best performance across all metrics, demonstrating the importance of these components for effective model inversion attacks. The authors proposed IFG-MI, a novel model inversion attack that effectively operates in out-of-distribution scenarios. By studying the structure of the generator and decomposing it into hierarchical layers, the attack extends the optimization space from latent codes to intermediate features, resulting in stable and high-quality image generation. To prevent low-fidelity image generation, a L1 ball constraint was applied to the optimization process. Extensive experiments demonstrated that IFG-MI achieves state-of-the-art attack accuracy while generating samples with high fidelity and diversity. This exploration of enhanced utilization of intermediate features in GANs contributes to advancements in the model inversion attack field, potentially leading to more practical applications. The authors hope this research raises concerns about the privacy leakage risks of released pre-trained models and encourages more responses to the threat of model inversion attacks. This research is supported by several funding sources. The primary support comes from the National Natural Science Foundation of China, under grant numbers 621711248 and 623011189. Additional funding is provided by the Guangdong Basic and Applied Basic Research Foundation, under grant 2021A15151100066. The research also benefits from the support of the Shenzhen Science and Technology Program, with grants JCYJ 202208181010102025, RCBS 202210080931240061, and GXWD 202208111729360001. Furthermore, the PCNL Key Project, PCL 2021A07, has also contributed to this work. Thank you for watching.